Hi, yes, my name's Frank Winiberg. I work at JPL, and yeah, since last year I've been working on the airborne scanning microwave limb sounder instrument. And yeah, I just wanted to sort of preface this by saying I'm a little bit nervous because I'm kind of an imposter. Up until last year I worked mainly on UV visible in situ detection experiments in a lab. So there's many many different aspects to this project that I'm not used to. So yeah, the airborne scanning microwave limb sounder, I guess rather obviously it's a microwave limb sounder that goes on an aircraft and scans with a movable mirror. It's designed to fly on the ER2, and some of our main targets are ozone, water and CO, measuring around 340 gigahertz. So like I mentioned, there's a scanning mirror which allows us to sample 300 kilometer wide swath in the UTLS in front of the aircraft. And we're still going through the best way to run the scanning mirror, but in the sort of nominal mode, making a vertical limb scan every about 1 second and an azimuth sweep every 45 seconds, should be able to sample the atmosphere sort of every 10 by 10 kilometers in the horizontal. So picture of the ER2 obviously on the right, and then this is a sort of sample track over California showing that we can sample pretty much across the whole of California as we fly by. So the objectives of the instrument itself and the project was to try and address some questions around small-scale atmospheric processes that have larger global impact, and a couple of those are convective outflow and tropopause folds, which we've heard a little bit about today. And so on the right, it's just an example there of a model showing that this deep convection from the lower troposphere can push pollutants and things up into the upper atmosphere that can stay there for a long time. So the idea is to try and probe those type of phenomena. ASMLS itself measures around 340 gigahertz, so this is a sample spectrum in the observation window, and so yeah, we can see a whole bunch of lines from things like water, N2O, ozone, CO, and it employs much the same technique as the Aura MLS instrument, but with slightly different receiver technology using low noise amplifiers, which combined with their improved signal to noise and the slower speed of the aircraft flying along, we're able to do a 2D scan of the atmospheric limb. So yeah, we can play with the sideband sampling for the instrument to look at different lines in this spectral region, but right now we're focusing, as I said, on water, ozone and CO, and so on the top of that spectrum there are a couple of black bars, and that's where we're positioning our sampling right now. So just to sort of give you an idea of our expected performance, have this nice bar chart on the right-hand side. And so the idea here is these are a range of species we might be able to detect, given a typical concentrations and a signal-to-noise of about a factor of 10. If you take a look at the graph, you can see around 100 milliseconds as a green line, so that's in our sort of like nominal 10 by 10 kilometer horizontal sampling. Should be able to sort of easily detect ozone and water, and then if we integrate for longer, we should be able to see a wider range of species. So in a very simplified block diagram kind of way, we've got this 2D scan mirror on the front of the instrument. That feeds light towards the receiver. We have a switching mirror in between the receiver and that scan mirror that allows us to look at a couple of calibration targets. And then the signals from the receiver are sent through an intermediate frequency processing slice and then read into a couple of digital spectrometers that feed the data into our computer. So the receiver itself operates at about 70 Kelvin, but can run at room temperature, obviously with a increased amount of noise, but yeah, I guess I put that in there because, you know, haven't flown the instrument in this configuration before, so if the cooling doesn't work, it should still work. We should still get some data. So a sort of brief ASMLS history lesson, I guess. The instrument's been in development since sort of mid-2000s and was originally designed for the WB-57, not the ER2. It goes in this spear pod. It's based on more closely to the AURA-MLS technology, centered at 240 gigahertz. And it used this 4 Kelvin liquid helium cooled cryostat to keep the detectors nice and cold. And so, yeah, you can see a picture on here with Bob Snapnick on the left, who was ostensibly in charge of the instrument up until recently. And I don't actually know who's filling the dewar with liquid helium, but yeah, it sounds like a right pain in the arse. So I'm kind of glad we moved away from that. Anyway, after that, they moved away from the WB-57, adapting it for the ER2, but we can still keep it in the same chassis, in the same rack, because the ER2 has this adapter ring that allows us to run the WB-57 instruments on there, which is great. And then they switched out those receivers to the 340 gigahertz LNAs with the 70 Kelvin cryostat. The problem was with this configuration is that the instrument was a bit too heavy, and so we've ended up moving some of the back-end electronics, spectrometers and stuff into the mid-body of the spear pod. So we're kind of spreading ourselves out luxuriously all through one wing pod, unlike most instruments that fly on the ER2. And then there was an optimistic timeline proposed for sort of mid-2020 to do some test flights with this new configuration. Obviously that didn't happen for various different reasons. And then once the project was back on track to fly in sort of the January timeframe of 2022, Bob Snapnick retired, and they found the next victim to take over the instrument, myself. Yeah, we were supposed to fly in September of 2022, and we turned up to Armstrong with the instrument, and as we arrived, I think it was the guys who run the Pickard instrument, they laughed at us coming through the door and said the engine's broken and the plane's not flying. So yeah, we're back on schedule for August, and then I wrote October we're supposed to fly with you guys, but I guess it's November, I got that wrong. But yeah, I'm really looking forward to doing that collaboration, and hopefully we get some good complementary data, and hopefully the numbers match. So the sort of another block diagram, component block diagram of the instrument. So we've got the spear pod up the front, got our scan motors and the scan control, the receiver, and the cryocooler, which also needs to be cooled itself, ironically. And we have these sort of cooling fins in the adapter ring, and then behind that in the mid-body we have our electronic chassis. And so this is a figure taken from the latest review that we have to show the progress of the various upgrades. So what we're still working on at the moment is the scan control system, so I'm going to talk about that in a bit more detail in a minute. So here's an actual picture of the instrument up at Armstrong, not flying but being weighed. And so you can see on the front, on the right-hand side, we've got our scan mirror on the 2-axis gimbal, focusing mirror that sends the light into the instrument, and then behind it, there's the microwave receiver, which is sat inside a vacuum chamber. And on top of that, there's kind of like a little black piece that green arrow is pointing to. That's the cryocooler. And then the big sort of gap towards the back of the instrument is where all the electronics used to sit, but they're now in an electronic chassis. And yeah, we have an aircraft heading and gyro on the back there to account for any pitch and roll variations in the instrument. That's hopefully going to feed into the scan motor electronics shortly. So then this is the mid-body with the electronic chassis sat in there. The engineer was pretty nervous who built the box. He didn't think it would fit, but it does, so that's good. And then on the right-hand side, you can see the adapter ring that takes us from our narrower spear pod out to the super pod body for the ER2 wing pod. And on there is one of our coated cooling fins that will wick heat away from the cryocooler. And this is just another view of the instrument testing in the lab. Obviously, even something that just flows some kind of thermofluid through it is a closed loop system and therefore a pressure vessel, and so I had to get it pressure safety tested. So that was, you can see we have a number of different fins, so depending on the cooling capacity required, we'll be able to put a number of different fins on that adapter ring. So what's next? We need to perform a full front to back calibration of the instrument. That's currently ongoing this week. And we'll also be looking into the data subsetting and compression so that we can have a live downlink of the data coming to the ground whilst we're in flight. And they're still working on the development of the ground data processing algorithms and software. One of the major things we need to tackle is like an active pointing system so that we can account for any changes in the aircraft pitch and roll. So I'm just going to go into that in a little bit more detail. So ASMLS is going to be looking out at the limb some 300 kilometers away, and this obviously requires quite a stable platform to take accurate limb measurements. And so the ER2 itself is an exceptionally stable platform, underlined because I don't want anyone to take away that I'm like dissing the ER2, but it does see, as you can see from the plots on the right, these small variations in pitch of about 0.5 degree. So on the far right, you can see there are some changes on the course of tens of minutes to hours as the aircraft flies along, and then in that little inset where the arrow's pointing, even on the sort of 5-minute time scale over which we'd be making our measurements, you do see some slight variations, and so we would ideally like to be able to correct for those in real time. And so, the main problem with this is that if we kind of have the dumb mirror system that we have right now, we're going to oversample the limb. And so what we're working on is real-time pointing of about 0.5 degrees to ensure that we minimize the data loss due to that. So that's what I'm working on at this moment. Which turns out to be more challenging than I originally expected. So that about wraps it up. So I'd like to thank the team at JPL who took over the ASMLS instrument. It's a really good mix of people with different background experiences and people at AFRC who have been amazing in helping us get the instrument qualified for flight, and also the Upper Atmosphere Research Program and the AITT that have funded the instrument and the type of science that we want to do. And with that, I'll take any questions. Thank you.